start. Hi everyone, thanks for joining. It is my pleasure to introduce speaker for today's colloquium, Professor Santanu De. So Professor De is a professor at Georgia Institute of Technology in the Department of Industrial and Systems Engineering. Professor De's research interests are in the area of non-convex optimization and in particular mixed integer, linear and nonlinear programming. Professor De has won numerous honors and awards, some of which are IBM Faculty Award, Class of 1969 Teaching Fellow at Georgia Tech, NSF Career Award, Informs EANRI Best Paper Award for Energy, and the Informs Optimization Society Ballas Prize. So today, Professor De is going to talk about solving STPs by using sparse linear inequalities. So let's hear from Professor De.
Thank you. Thank you very much, Akhilesh, and thanks everyone for this invitation. It's I've already spent fun time talking to friends and discussing optimization. All right, so let's get started. Solving STPs by using sparse linear inequalities. Folks usually talk about theory and computation, and I talk about computation and theory, and that's because that's how I've ordered the talk. I'm going to first talk about some computational work, which motivated some theory questions, and then we'll see some results that we obtain along the way. So the first part of this talk is joint work with Alex Kazakov, Andrea Lodi, and Gonzalo Munoz, and this is about creating lightweight approximations of SDPs. So let's get started. All right. So everyone knows what SDPs is, but let me just just the notation. So this is what SDPs look like. The variables are matrices. The C in AI here is data. BI is data. This is the so-called trace inner product. All these matrices here are supposed to be symmetric, and so the trace inner product is nothing but just sort of term by term products of these matrices, and if we did have this X is in Sn plus, this would just essentially be a linear program. But this additional condition says that this matrix here has to be a Psd matrix. And again, what is that? We all know Psd matrices are symmetric matrices. When you compute the quadratic form for any corresponding to the matrix for any vector, it's non-negative for all vectors. And this is the same as saying, for example, all the eigenvalues of these matrix X, for example, are non-negative, and so we know this. And again, STP is is a class of conic programs for which there is polynomial time algorithm, and there's very beautiful theory, but unfortunately, sort of from a practical point of view, there's still problems that are sort of difficult to solve in some cases. Now, my interest is more in sort of integer programming and MI&LP and global optimization, where usually I'm not thinking of SDP program as the problem to solve. I'm thinking of it as sort of a convex relaxation of some more difficult problem, a more difficult integer program, or some polynomial optimization, or some such thing. And so really what I'm thinking of is that I want to construct this SDP relaxation because it's a very tight relaxation, but then I probably want to do branch and bound. And if that is the setting, then just maintaining and solving an SDP at each node of my tree is really difficult. And so the motivation of this work was that can we trade off this sort of difficult problem to solve computationally? And again, I'm not really an expert, and there are methods to scale SDPs and so forth, but can we sort of replace it with essentially a linear program, because linear programs have sort of nice properties, you can warm start easily and so forth. And you want to replace the SDP with an LP, but that gives you essentially the same amount of bound, same bound tightness, right? So that's what you want to do. All right, so how do you do this? So let's think about it. As I said, if we just remove this constraint here, that X has to be in this PSD cone, then what results is an LP. But of course, if you did this, you lost all the strength of essentially having this SDP in the first place. And so what you can do to tighten this LP and make it sort of get bounds closer and closer to your original SDP is the following, right? You could solve this LP. Let's say X tilde is your optimal solution. If of course this optimal solution was Psd matrix, then you know that you essentially get the same bounds, right? This is with the upper bound meeting the lower bound. But if that doesn't happen, what would that mean? That would mean that, well, this matrix that you got by solving this LP without this Psd constraint was not a Psd matrix. In other words, it must have had at least one negative eigenvalue. So let's say lambda 1 was this negative eigenvalue corresponding to the eigenvector v1. Remember, this is the standard decomposition of the matrix, right? Of any symmetric matrix, you will have real values here, but now because of Psd, it's negative. And again, this is all well understood. So what you do, you take your matrix V, which is the outer product of this eigenvector corresponding to the negative eigenvalue, and it's easy to see that V times X inner product with any matrix which is in this cone is non-negative because this itself is a Psd rank 1 Psd matrix. But in fact, with this X tilde, because of the way things work out, this is exactly equals to this eigenvalue, which is negative. And so this gives us a separating hyperplane. And so we add the inequality V times X is greater than or equals to 0, and we can repeat that. And so, but notice this is an LP, and every time I repeat this loop, I add linear inequalities, and so I maintain it. Okay, is this clear? Any questions? Okay, so that is the setup, right? So let's see what happens. Let's try this. Okay, so let's apply it to a class of problems, polynomial optimization problems. In fact, quadratic programming problems called as the box QP, which is just saying minimize a quadratic form such that the variable is between 0 and 1, continuous. Okay, and of course, if Q here was a Psd matrix, this would be a convex program, which would be easy to solve. But we assume Q is not a Psd matrix, and so it's not a convex program. And so first, let's quickly, and again, this is something that just for notation and just to see an example. So how, for example, how do we solve this problem? Well, how do we get tight relaxation for this? One relaxation is the so-called STP relaxation again. And so this problem is rewritten in this form. It's the same thing. X times Q times X is nothing but the inner product of Q times the XX transpose. And now once we see that this is this form, you can rewrite it in this form where you introduce a new matrix variable, which is supposed to be the outer product of your variable X times X transpose. This is your matrix variable, and so this is the problem to solve. This is equivalent to the original problem. So this is still non-convex, and so you get the convex relaxation by saying that now all the non-convexity was in this constraint here, capital X is X transpose, so you relax it. And again, and I'll not go into the details, but you get a bunch of linear inequalities. These are the so-called McCormick inequalities. And you can also say that this matrix here should be in the Psd cone. I guess I should have put an n plus 1 here. So there's originally was n. But yeah, that's a typo. But this problem here essentially is of this original form. It's of this original form, and maybe this is a relaxation. I could solve this at my root node, and then I could do the so-called spatial branch and bound, and actually solve this problem as a branch and bound, where at each node I solve a problem that looks like this. But this is, of course, very expensive to solve and difficult to solve, and so basically I'm going to work through one instance. I'm going to look at this one instance, which is by Sam Buehler throughout the talk. I'm going to use this one instance of this problem, and let's see what happens. If you are interested, the numbers mean here 125 is the dimension n, and this 25 means that this Q matrix here, there are 25% non-zeros. Okay, so it's a sort of relatively sparse matrix. Okay, so this is what we see. Okay, is that so this is essentially what I'm doing is I'm applying this cutting plane approach, right? I basically ignore this constraint. I just solve the problem. I get X tilde. I then define the separating hyperplane from the Psd cone by looking at the eigenvalues like we discussed and add it, and then we keep repeating this, and we see a performance. Okay, so initially it kind of does well. but you see that there's a tailing off effect, and this is 75% off from the. So there's a question. So that's a great question, Jeff. Yeah, so I think this right now, these experiments, we are actually, in fact, it's more than one cut at a time. It's actually one cut per negative eigenvalue. So even with that, so one cut at a time would be even worse, but even one cut per negative eigenvalue, actually, yeah, you see this sort of tailing off. Okay, did I answer your question, Jeff?
Yes.
Oh, thank you. And so okay, and so and again, this is, we're not the first ones to observe this. This is well known. People have seen this before. And so what do you do? Okay, so and you do a little bit. You dig a little bit into numbers. What you notice is that this is the solve time. I'm plotting here times of the LPs as you go with this computation, and you see that as the time of your computation, as the iterations go progress, these LPs become more and more and more difficult to solve. Okay, and so the idea is, can we reduce the time of these LP solves? Maybe that's sort of one bottleneck at least you can try and remove from solving this Psd, by adding these cuts. And so how would you do that? All right. So let's see why these LPs become difficult to solve. My n was 125, so the LP, it's symmetric, so it's not exactly n squared, but you basically have that many variables essentially. And so typically what happens is these eigenvectors corresponding to these negative eigenvalues tend to be dense vectors. Okay, and so what happens is that when you're adding this inequality, this is a dense inequality. Essentially, all entries in this capital V are actually non-negative, and so you have already basically an LP with, let's say, about 10,000 variables, and now each round you're adding this cut with which are non-zero in all the entries. So the LP is fast becoming really dense, not nice. And really what you would want to do is keep away from dense inequalities. You want to use sparse inequalities as far as possible, because LP solvers love that. There is a lot of very cool work with using sort of sparse linear algebra to exploit sparsity. All right, so how can we do this? Well, the answer is, instead of building just a linear programming relaxation, what we want to do is build a sparse linear programming relaxation. So the inequalities that we want to add, they are going to be separating from your SDP cone, just like earlier. But the separating inequalities that you want them to be sparse. So remember earlier, we for our x tilde, that was the solution, incumbent solution of our LP. We found an eigenvector V such that this product was negative. Now, maybe I don't care about necessarily the eigenvectors. I just want a vector V where this is negative, but this is just modern notation to say that basically I want this vector to be sparse. That is, for example, this inequality means that I want no more than some prefixed value k of the entries of this vector V to have non-zero entries. So if I do that, if I'm able to find a vector V of this form, then I will be able to separate my current x tilde from the Psd cone, but the inequality that I add is sparse. Okay, so the questions are, how do we do this? How do we find these sparse eigenvectors? And once we do this, does it actually help? All right, all right, so and again, this is not the first study of this kind. There are some very nice papers by Kulitsa, Belotti, Margot, and then Radu Lugian, Pierre Bonami, Ruth Meissner, and Rata Bantani, and this somehow you could say follow-up work on this. So inspired by these guys. All right, so how do we come up with this sparse relaxation? All right, so again, so what is our goal? We have this x tilde, which is not all its eigenvalues are not negative. It's not a Psd matrix right now, and so we want to find a vector V such that this quadratic form is negative. Okay, I've just added this. It doesn't matter. I can rescale a vector. It's a Euclidean norm, but I also want it to be sparse. Okay, so I want to solve this problem, and it turns out one way to solve this problem is to actually look at the sparse PCA problem, which is not surprising, actually. It's all related. what is a sparse PCA problem? Basically, you work with a covariance matrix. So this is this X bar here. And what you're looking for is trying to find a vector V, which captures most of the variance. But that's just saying you're trying to maximize this quadratic form subject to this. The sparsity comes from the fact this vector V should be sparse. And again, scale the problem. So it's 2 norms. Very good. It turns out these 2 problems are essentially equivalent, even though this X tilde here is neither Psd. No, it does not have to be negative definite or positive definite. It's a simple sort of affine transformation, and we don't have to go through the algebra. It's very easy. But basically, there's a very simple observation that if you take your current X tilde matrix and you apply some affine transformation, you take this new matrix. This is actually a Psd matrix, and you find it's you solve the sparse PCA problem on it, and depending on the value of the sparse PCA problem, you either can find a sparse separating inequality or not. Okay, as the optimal solution of the sparse PCA. So there is a very simple transformation, and so basically, we can just use sparse PCA. Okay. So as a side note, so this is what we want to do, and I would say that I referred to papers before who've also tried to use this sort of sparse inequalities, and they had other ways of trying to separate these sparse inequalities. Okay, and so this is sort of what we did differently here. But the question is, okay, so we want to use sparse PCA, but can we solve sparse PCA well? As it turns out, unfortunately, theoretically, it's a hopeless problem. Okay, they're inapproximable results. In fact, the best approximation guarantees are like n to the third. Okay, so in some sense, it's really a hopeless problem to solve. There are some nice fixed parameter tractable results, and there are some very nice extensions by Alberto to extensions of sparse PCA with more complex constraints and sparsity and so forth. Basically, these results, this family of results says that you can solve the sparse PCA problem well and efficiently if the rank of the matrix is fixed or it's low. Basically, the running time is has an exponent with the rank, right? So that's what's going on, and we've also looked at some more sort of computational methods together with Rahul Mazumdar and Kwani Wong and Wei Jun at Virginia Tech together with Pages Rune. And there's some other more computational methods to kind of solve these problems exactly or within some like 5 to 10%. And we can sort of computationally solve these problems, but even solving one instance and giving bounds takes a few hours. Okay, so this wouldn't work to separate one cut. But as it turns out, in the ML community, there are these heuristics, which from what I understand, again, I'm not an expert in this area, they come with very little guarantees. Or they come with guarantees under very special situations, but they work really well. And honestly, in our computation, not only they work very fast, they work very well. And they're essentially adaptations of, if you know how eigenvectors and eigenvalues are numerically found out, one of the methods is the so-called power method that you learned in your first linear algebra class. And this is just adaptations of this method. So you do the power iterations, and each iteration you again sort of truncate your current solution and then repeat in some sense. And they just work amazingly well in practice. Even though, as I said, there is, as far as I understand, there aren't really many guarantees. There are some guarantees in special cases. Okay, so this is what we really use. And so let's look at our experiments again. And so again, the story is I want to solve the SDP, but I really want to create an approximation SDP that I'm going to use within a branching function, right? And I want this to be linear programming relaxation, which hopefully has similar bounds as SDP, but the linear programming relaxation is much easier to do, right? That's what I want to do, and that's why I want to use sparse inequalities. All right, so this is our first experiment, and this is and as you can see, Jeff. I didn't share my slides with Jeff. Jeff already knows about this stuff a priori. This is what happens if you try and add one sparse cut at a time, and you see that this was the same instance, right? At 75%, it's kind of the dense kind of start dying down, but the sparse kind of die down early. If you kind of look really hard at this picture, you see that this yellow line has an angle which is slightly better than the brown line. Now it turns out for smaller instances, what we see is that within an hour we see something like this happen. Okay, we actually see that the sparse cuts eventually take over the dense cuts. But for example, with 125 n equals to we don't see this behavior within even an hour of computation, and so of course we realize that one cut per iteration is not good, and so we have some, and I've decided not to present it here, but we have some sort of reasonable way of generating multiple cuts each iteration, and once we do that, this is what we get. This is the green curve you see, and you see that within an hour we are already beating sort of the dense cuts. More importantly, this is how the LP solve time goes. So remember, with the earlier dense cut, the LP solve time kept going larger and larger, and that's why somehow the number of iterations was slower and everything was stalling. If you just use one sparse cut at a time, of course, the LPs, the runtime just basically doesn't increase. When you add multiple cuts, you get something in between. But it seems that this also kind of stabilizes. All right. So even though you add multiple sparse cuts each iteration, the runtime of these LPs don't increase as much as with the density quality. So things remain in control, and that's why you see this behavior. Because this is plotted with respect to time. So the number of iterations that the green algorithm is having with respect to the brown is much more, because the LP solve times are much lesser. Okay, so that's what's happening. All right, and okay, so we can do some more engineering. We realize that if you look at all of these curves here, the dense cuts give you like this. The first round, the dense give you this bang for buck that you just don't get. Okay, with these sparse cuts. So we said, okay, let's do a little bit more engineering. Let's add dense cuts for one round, which is expensive, but hopefully that doesn't hurt the LP solve times too much, and then sort of apply sparse. And so if you do that, you start, we get sort of this blue curve where we get this advantage of the dense, and then we start improving on that. And you see here, actually it turns out this hybrid method, the LP solve times kind of remain the same as the sparse. And so again, we're exploiting the sparsity of the underlying LP. We are not, the LP solver is, and that's helping us to do more iterations. And so we are actually able to close more. And there are more extreme cases of this. This is some other instance where you see that we basically close almost 100, at a much faster time compared to this sort of dense cuts. Here you see the performance of the hybrid much better than the others. Of course, the gap closed is not so high, but with respect to the dense, it seems to do much better. Okay, I'll not go into more details of this. Let me just quickly show you some final computational results. So these are the BoxQP instance, and we go up to 250, which is fairly large, fairly difficult. And here you see that the gap close with respect to the SDP is quite high, and the hybrid is doing quite well compared to the dense. And you see that the solve times are actually quite nice. Even like these instances are really difficult. The experiment is run for 1 hour, but these are the times for the solve times for the LP for the last LP that we have, like with all the cuts. And you see that this is about 500 seconds. And just to contrast this, if you actually had to solve this LP and with Mosaic, and again, I'm not an expert in SDPs and interior point methods and ADMM and other methods to solve SDP. So there are certainly other methods to solve this problem. But if you just, if you were sort of a novice user like me, you picked up Mosaic, which is supposed to be a good solver. These instances to solve them to optimally takes much more than 1 hour. And in fact, the bigger issue is memory. So they take a lot of memory, whereas these LPs are, they're LPs. So the LP solvers, are much nicer. So this is somehow my best computational result. We can also do the same sort of thing for what is called this BIQ, which is basically the same instance. We've seen what the BoxQP instance earlier is, but now the variables are also binary. So you have some additional constraints like xi square equals to xi, which also you linearize, it's part of your constraints. And okay, the performance is a little bit worse. Notice that even the dense cuts don't do very well in approximating the SCP, and the hybrid kind of does what the dense does. All right, but in much, this is the final LP takes much lesser time than the dense. And here is some examples with max cut, and up to 100 nodes, you see that we do okay. But okay, this is certainly not a method that you should always use. Here you see that for these larger instances, the gap closed, even with the dense cuts, is really bad. So this cutting plane approach just breaks down, and the sparse also doesn't really help. Okay, so again, not to be always used, but there is certainly some value of trying and approximating your SDP upfront using some procedure like this, so that you get a cheap LP, and then maybe you can use this cheap LP to continue doing branching. Okay, so this is sort of the message of the first part, and so if there are any questions, I'm happy to take that. Otherwise, I'm yes, Jeff.
So if I understand correctly, you always built the full space SDP, like even if the Q matrix was 10% dense, you added variables. Even,
I think that's what we did, yes.
Yeah, and did you ever try to?
No.
Okay.
Yeah, no, we didn't try to. Yeah,
like
no.
Project on,
as I said,
finding inequalities that had coefficients only in that space of variable.
Yeah, no, of course the inequalities are no, we didn't do that. No, but we just did the most naive mosaic.
Okay.
Yeah, so there is But I mean, I'm told. Again, I am no expert on this, but for example, this when n goes to 250, this is these instances are fairly difficult. But I mean, of course, I mean you can solve them using your cuts, of course, which and in a different way. But yeah, okay, yeah, no, but again, I said this is. I'm not giving this talk to say that you shouldn't be smart about solving SDPs, and there are lots of smart different ways to do it. I'm just saying that within a context of a QCQP non-convex problem, this might be a reasonable approach sometimes. Okay.
Yeah, I mean the point is that if you are solving it, if you're going to do branching,
right,
in the Cplex, like you wouldn't add those variables if there wasn't a bilinear term for those for the product of variables, and so trying to find inequalities, whose support is only on the variables that you have in the problem, in your formulation of the problem.
Right. I think we are working with the full thing. So yeah, that is of course not mine. Yeah, that is certainly not.
Anyway, thank you.
But okay. But the takeaway for me from this experiments was the following surprising fact: when you add these sparse inequalities, or even if you look at the hybrid, the gap that you close with respect to the SDPs is almost the same, and this is surprising. You really, you don't expect that. I mean, when we started, we really expected that to have examples where essentially if you ran the dense really long enough, right, you would beat the sparse, which is in theory true, right, because the dense are supposed to approximate exactly the cone. But the sparse seem to do surprisingly well. Now, again, Jeff, you're right, and this is a setup, and that's a fair argument. But okay, but even then, this is an interesting and surprising observation. And so the second part of my talk is really trying to understand this question, sort of more from a theoretical angle. All right, so the second part of this talk is joint work with Greg Breckerman, who's a professor in math at Georgia Tech, Marco Molinaro, who's at Pocrio, everyone. The IP community knows him. Shendik Sun and Kevin Shu are PhD students in math. All right, at Georgia Tech. So all of the discussion till now was in terms of separating linear inequalities that are sparse. But if you think about it for a minute, essentially what we are saying is the following. This is the SDP that I wanted to solve. But now what I'm going to do is, instead of solving this SDP, I'm going to enforce the Psd-ness of this matrix S only in these k by k principal subminders. Because each of these separated inequalities that I get that have support of like on k variables, those are actually being implied by the Psd-ness of a k by k submatrix. Okay, so one way to understand this problem, which is sort of a little bit easier in some sense, is to say, okay, instead of trying to understand, what is the difference in gap between these two problems? I solve the problem with the full, the Psd constraint globally on the full matrix variable, or I just have like a lot of these, or a selected few of these k by k. And certainly in the computations, we're doing a selected few. I should have mentioned our sparsity level was about 25%. So if n is 200, 200 choose 50 is a very large number. We don't add that many cuts, right? So we're certainly adding cuts in some selected subsets of them, and as I told you, at least experimentally, these two numbers seem to appear to be the same, but are they? Can we understand the relationship? Okay. And as it turns out, this is a very difficult question to answer. We can't answer it. And so, friends who know me know that I always cheat. And so let's cheat and let's solve an easier problem, right? So let's get rid of the optimization problem. Let's get rid of the data. And let's ask, in some ways, a more cleaner pair problem. Let's forget about optimization. Let's just look at this cone of matrices, Psd matrices, with the following cone. It's a cone of matrices, and where every k by k, and I remove selected. So again, that becomes too complicated. I can't analyze that. So every k by k principal subminor is Psd. So notice this the one well-known property of being STP is that this property is invariant under taking like the principal submatrices, right? So principal submatrix, everyone knows this. Just so that I know, I look at the same columns, I look at a bunch of subset of columns, and exactly the same column I pick the rows, right? So that's a principal submatrix, and if your matrix originally is Psd, then this submatrix is also. But opposite is not true. And so what I'm saying is that essentially this cone of matrices, where I enforce every k by k Psd principal k by k principal submatrix as Psd, is a much larger, or it's a larger cone. But how much larger is it with respect to the Psd? Okay, so is this question clear? Right. So again, so if you are in this, if you are matrix in this cone, then every k by k is Psd. But if every k by k is Psd, doesn't imply they are in this cone, so it's a much larger cone. It's larger, and so we want to understand how much larger is this. And by the way, this problem has other directions and connections that people are interested in. It turns out this cone that we'll formally define and work with, the dual cone of this is it's a cone which is called as cone of matrices where the factor width is k. And I'll not go into the definition and so forth right now, but that dual cone is of interest to sort of the sums of squares community for other reasons. So this is a cone that is worth spending some time with and thinking a little bit about. Okay, and so let's move on. Okay, I have 10 minutes. Okay, so this is going to be interesting. All right, so we formally call this cone the k-Psd closure. And we did use this notation SNK, which is saying that matrices are n by n, and every k by k principal submatrix is Psd. And so we look at this matrix, and as we said, the question we want to know is how far is matrices in this from matrices to SNK. Every matrix here is it here, but there are matrices here that are not here. How far are they? All right. So whenever you want to answer a question of this form, notice first of all the question is unbounded, right? If I talk about distances, they're cones. So if there's a matrix that is in SNK, which is not in SN plus, well, if I just scale this matrix, it becomes infinitely away from the cone. So in order to answer this question, I have to normalize things. I have to sort of cut these cones. And also, I have to decide on some measure to define this distance. And what we'll do is we'll use the Probinus norm for both of them. So let me remind you, what is the Probinus norm of a matrix? It's just you think of the matrix as a vector, and it just find its true norm. Okay, it has other very nice properties. And so this is sort of, we decided this is sort of the thing that we can analyze. And so what is this? We look at matrices that are in SNK, whose Probinus norm is 1. So we're chopping off that cone. And then saying, what is the distance of this matrix from SN+, right? And then we want to find the worst such matrix. That gives us the distance of how far this cone is from this. Okay? And again, this distance we measure in Probinus norm. So it's really solving this problem. So find me given a matrix M in SNK, whose Probinus norm is 1. For that matrix, the way to find the distance is to find this matrix N, which is Psd, and finding that is closest in the Psd cone, and finding this distance in Probinus norm, and then sort of solving the whole. All right, so one quick property about this distance, and I put a bar because in some sense it's this distance matrix is that it's actually between 0 and 1. Why is that? Well, it is 0 if the two cones are equal. But if you take any matrix here, because I restrict its Probinus norm to 1, and since the 0 matrix is always in Sn plus, this distance can never be more than 1, right? So this distance is always more. But it's a measure. So if this number is close to 1, that says that this matrix is really much larger than Sn plus. And if it is 0, then they're the same. Okay? And so what we want to try and do is try and understand properties of this distance. Okay. So our main results are essentially bounds on this distance as a function purely of n and k. Okay. And so here's our first result. So this distance is upper bounded by this quantity here. It's not that interesting to look at this term here, but ignore the k minus 2 because that's just a constant sort of away from this term. So essentially this theorem is saying that this distance between these two cones is sort of linearly changing with k. Okay, so if k is n, this is 0 because you enforce everything on the k by k. If k is basically 2, for example, where you're only saying it's an SOCP, essentially, the factor is essentially n. That's what this distance is saying. As it turns out, this upper bound is better when k is small. That's what we observed. But when k is close to n, this upper bound doesn't work that well, and so we had to work a little bit harder, and we were able to come up with another upper bound. Again, ignore this complicated formula, but the way to think about this upper bound is the following: if n is really close to k, if k is large, so k is really close to n, this term here is essentially 0, and this k looks like n. So this is essentially like an n cubed term with a square root. And so it says that essentially this distance is n minus k to the power 3 over 2. So in other words, what's happening is that as n is, for small values of k, when you enforce PSDness on very small principal submatrices, and you change k, the rate of getting closer to the PSD is sort of linear. But as k goes closer and closer to n, now that is a regime that computation is not interesting. If I was solving the problem with 250n, I would never, try and do 220. I would, if I had to enforce on 220 or 230, I might as well enforce it on all 250. But since we are understanding this quantity, we want to understand completely. It turns out, it seems that when k gets closer and closer to n, the rate of getting closer to the PSD code gets faster, right? It looks like. And here's actually the two upper bounds exactly implemented for n equals to 20 and different values. And so you see, this is the first upper bound, and the second upper bound gets a bit better than the first upper bound with larger values of k. And you see this difference more with higher values of n. Okay. So we have two upper bounds, but how good are these upper bounds? So the way to say that is through lower bounds. So let's try and get some lower bounds. And how will we get lower bounds? The proofs, and I don't think I'll have time to discuss the proofs, but some of them are complicated, but essentially a lower bound just comes from actually giving a class family of matrices. So you have to construct a family of matrices and compute its distance, and that gives you a lower bound, right? That says you're at least so much distance. All right. So the first result is this lower bound, and again the formula is complicated, so ignore it. But let's parse through this formula. So let's say what happens when k is small. So if you look at the denominator here, we have this k minus 1 square n. But if k is small, this quantity is really small. So this quantity is dominated by this n square term. We have a square root. And so this looks like n minus k over n. So this tells you that if k is small, the upper bound that we had is basically that. Okay? And let's look at the other regime. If k is really large, k is essentially a constant away from n. Okay, now let's look at this term again. Now notice that this is n square, but this k looks like n. So this is sort of an n cube. So there's a square root term, and so essentially you get this distance, which looks like our upper bound from the second term. And so this lower bound is saying the two upper bounds together do quite a good job when k is small and k is large. Okay, and here's how they look like. So this was the first upper bound, this was the second upper bound, and this is our lower bound. And you can see that when k is small and when k is large, we kind of know what this distance really is. We've kind of nailed it. it's in the middle region we don't know what's happening, right? In the ideal world, the lower bound that we get is the right lower bound, because that would say that these distances are small, and maybe that would argue that this is why we are seeing what we are seeing in our computational experiments, where the sparse and the dense really don't matter so much. And in fact, explicitly stating this, if I take k to be a constant times n, let's say 0.5 times half, right, or 0.25 like we did in our experiments, our first upper bound essentially looks like 1 minus r, and the second upper bound, I didn't do the calculation here, is also a function of r, independent of n. Whereas our lower bound, as it turns out, goes off to 0 as n goes to infinity. So our lower bound is saying that in this regime, when k is 0.25 times n, as n gets larger and larger, essentially the two cones become the same. Whereas our upper bounds are saying there's the gap, and which one is the right answer, right? Unfortunately, I mean, as much as we would like the lower bound to be the right answer, unfortunately, that's not true. Now, this result again has lots of ugly constants because it's a probabilistic proof with some things going on. But essentially, what it says, okay, this r is quite small, but for some values of r, if k is this r times n, then there is a family of matrices whose distance is a function only of r and independent of n. So it's not true that this lower bound that we have is indeed somehow weak in this region. Okay, and the yeah. Now this number here, does it match our upper bounds? No. And so this is certainly an open question. But unfortunately, it kind of says that if I had to guess, I would say that this first upper bound is the right kind of, if you wanted to get a measure, unless you get really close when k is really large, and then you need the second upper bound. But it seems that this is right. Okay, I have only 1 minute left, so I'll mention one result. One thing is, these results certainly don't say that sparse cuts should do as well as dense. It tells you a little bit about what is happening, but not so much. But there is one more observation, right? We got the strength of our sparse cuts by essentially adding sparse cuts on very few supports. Okay, can we explain this behavior? It turns out that at least this behavior we can explain, and here's the result. Okay, so again, our k and n is as it is. Okay, I see a question here. Oh, thank you. I can go up to 1250. Okay, so I have, okay, so maybe I can show the proof of the first upper bound, which is really clean. But okay, so let's take this result. So pick your epsilon and delta suitably small, but as constant parameters. So then this number m here is essentially looking like n squared log n. Okay, I'm cheating because there's this epsilon squared and delta, but okay, for fixed values of epsilon delta, this is essentially n squared log n. So this is nowhere close to n choose k. Right? Let's say if your k was 0.25 n, and choose k is a much larger number. And here's what you do: pick m rows and columns, sort of uniformly sampled from all these possible principal. So you have these many different principal sub-matrices. Among them, just independently and uniformly sample m of these principal sub-matrices. And then you consider this random cone where you enforce the Psd-ness. This is notation for enforcing Psd-ness. You enforce the Psd-ness only on these m randomly selected supports. Okay, or each of size k, right? Each of size k. Then one can show that the distance of this random cone with high probability, so basically 1 minus delta probability, is this quantity. And this green part here, if you'll recognize, is our first upper bound. So it's basically saying you add n squared log n of these guys, then you essentially get the power of the full thing. And this is a little bit more believable result. Why? Because if you think about it, when you enforce this Psd-ness, right, these matrices are like overlapping on each other. And basically what it's saying is that you don't really need to kind of like take all this n choose k guys. You kind of take sort of n squared or n cubed, let's say, of these things. You are getting enough coverage that you kind of get the same strength as you got from n choose k. All right, so there was a question, I think, and no, okay. Is there any question? Okay. All right. So if there's no question, let me try. I have 3 minutes, and so let me just try. And so at least the first upper bound is really natural, really easy. So it explains why it's such a good upper bound. So let me show you this first, the proof of the first upper bound. Okay. So I have this matrix X in SNK, right? And let's say this is my K by K principal submatrix. By definition, this is a Psd matrix. The submatrix is a Psd submatrix. So here's what I'm going to do. I'm going to take this matrix X, and I'm going to construct this new matrix where I just zero out everything else. Okay. Now it's very easy to see that because this original submatrix was Psd, this whole matrix is Psd. Okay. Now here's what I'm going to do. I'm going to take an average. So I'm going to take every subset, principal subset K, and for every principal subset K, I'm going to construct the zeroing out operation, and then I'm going to take an average all of these guys. Okay. Now average of Psd matrices are Psd. It's just a convex combination of Psd matrices. So what happens is I start with a matrix X, and I get this averaged out matrix that is in the Sn plus, right? And if I find the distance between these two, this gives me an upper bound to the distance on the Psd code. It turns out that this average matrix has some very nice properties. It looks exactly like X, except that the diagonals and the off-diagonal terms are scaled differently. It's essentially, when you do the math, you'll see that basically you get something that looks like X. It's just that the off-diagonal terms are scaled a bit differently, and the diagonal terms are scaled a bit differently. And because of that, you can actually really compute the Probinus norm. You take the difference of the matrix and compute the Probinus norm explicitly, and it turns out to be this quantity. And so that's I think this is a good place for me to stop. And so I will run through all of this, and thank you very much. Are there any questions I can answer?
Please feel free to unmute yourself and ask questions.
So can you say how the entries are scaled? I mean, there is like an entire, so you say the diagonals are this average matrix, like do you scale like the rows or the columns or both?
So there's a little bit more algebra, but if you see what happens, how often does this entry get used? It's basically, it's the combinatorics, right? You look at it's essentially n-1 choose k-1, whereas an off-diagonal term is essentially n-1 times n-2 divided by k-1 by k-2. It's one of those things. That's the number of times you would use that in the average, and that's how they're often. So basically, the diagonal gets scaled more, and that's why the matrix enters the Psd code. So notice, because this is a Sn k and k is always like 2 or more, these diagonal terms are always non-negative. And so basically when you do this averaging, the diagonal gets scaled more, and so it enters the Psd.
I was thinking that you would have to like push it based on like Gershgorin circle type ideas, but that's
yeah. No, you're right. That essentially it turns out that the kind of bounds you get from here are sort of similar, which you will get, but this is just a cleaner proof with this bound. You're right. But you're right. Yeah. It is essentially something similar. You're right.
Because does this have anything? I was wondering. So where do you use this fact that the dual cone, which is this thing that has something to do with like DSAW, like this?
Oh, we never use that. We never.
Oh, you never do. Oh, okay.
We never, in none of our results we do that. It's just that the dual cone is something people worried a lot about, and this is the other cone, and no one actually studied properties of it with respect to it. So that's, but okay. In none of our proofs we use that.
Okay, thanks.
So Santanu, I might have a very naive question. Can you go back to the slide where you define the distance?
Right.
Yeah. Oh, Maybe it was the previous one. Sorry, the one. I mean, the one where you crossed out everything in red and you simplify. Yes, here. So I mean, essentially, if I understand correctly, you are focusing on the different. I mean, you want to understand how different these two cones are, and this distance is a measure of that.
Exactly.
But if you consider the optimization problems, I mean, if you go back to the optimization problems, you are trying to minimize something over this feasible region.
Right.
So I'm just thinking, you know, about two polyhedra, for example. One is the relaxation of the first. It might be that the relaxation is much bigger than...
I agree. So in a sense, that's perhaps why the computational results are the way they are. You are absolutely right. In some sense, when you just compare the code and you're trying to find the farthest matrix, you know, this is somehow sort of the worst case scenario, right?
Yeah, you are very pessimistic. Like you are really looking at it's like looking at every possible objective function, essentially.
Exactly. In some sense, you're right. Yes,
yeah,
absolutely.
Yeah.
So yeah, and that's perhaps why the computation work better than, you know, the theory suggests. Theory suggests that somehow, you know, it's sort of as k increases, you sort of linearly, you know, if you believe the upper bound 1 is the right answer, you sort of linearly get better. Yeah. But as I said, in the computations, it's just, you know, you basically get in 1 hour, whatever you get from dense, you kind of get from the sparse guys. It's you know, okay, and with the hybrid, you know, it's really, everything is close. So, yeah, and so what you're saying is probably the explanation. Exactly.
Yeah, or maybe to take care somehow in the analysis of the objective function. I mean, to understand.
That's a good question.
Yeah.
It is, yeah, because you see, there are some very, you know, that's a very good question, because in a sense, it is, you're right. The largest distance matrix. It's not like, it's somehow very strange. It's in most directions, actually, it is true that this might be better. So yeah, a different analysis where you even like average it out or something would be, that's a good question. Yeah, that's a very nice question. Yeah.
Okay, thank you.
Yeah.
Santanu, could you say a little bit about the proof technique for the last result you presented in terms of taking a random selection of the k by k?
Oh, that one, I actually don't have the proof written there, but that actually is just simply like taking like union bound. Basically, it's the same proof that I just showed. Essentially, what happens is that, let me just state, let me go to the result. Essentially, what happens is that you look at, let me get this right. Right. So what happens, basically what you argue is the following, right? You look at this cone, and so now, earlier I was taking an average of all the n choose k guys, right? The proof I just did, right? I took every k by k principal submatrix, zeroed out the stuff, and then I took the average of all of them, right? Now what you're going to do is you're going to do the same operation, but over these m random supports, right? But then basically what you argue after that, and again, this is not so difficult, some simple algebra to show that, you know, basically within this error term, you are essentially, you know, so you basically argue that you're within the, even when you take term by term averages of just this many guys, the number that the average out matrix looks basically very similar to the average if you took all the n choose k guys. That's essentially the proof. I don't think I did a good job, but did I? But Jim,
I get the rough idea. I got.
Yeah. Essentially, that's the proof.
Okay.
So it's really the same upper bound proof, but a little bit more calculation. So and if you, I mean,
So sorry, Santanu, but when you explained that, you essentially said that these k by k minors that you take at random essentially ensure you appropriate coverage. So it seems that you're trying to cover your
Yeah, essentially that's what happens. You get appropriate covering and basically argue that the numbers that you get look very similar to kind of if you were averaged out. Again, because so and therefore we get something. Exactly.
So maybe you could, I mean, I guess that maybe you could achieve the same coverage, let's say, maybe with a smaller number of minors, but then you would need to optimize the way you pick them. And instead, if you pick them randomly, you need maybe a slightly higher number.
No, exactly. And in fact, and Jeff is asking what next. And that is something that we looked at. We couldn't get anything clean that we could say. But you know, there are actually, I mean, there's this area in statistics about these covering designs, and actually there are some connections to that. So there are certain covering designs that give you exactly the same upper bound as this upper bound, because the average things, you know, you don't need to have all those terms to get the same average. Okay, it's just that those covering designs don't. I believe. It's an area of research, right? So they don't have it for every choice of N and K.
Yeah.
And so that is, so we explored that a little bit, but then we didn't get anything substantially interesting to say. And but that's great.
Yeah. I guess that what you're saying is that it would be interesting to have like a scheme to pick up the minors and to ensure.
That would be awesome, right? Okay, you gave me an SDP, and I just knew a priori that these are the subsets that I want to enforce.
Yeah.
If I could do that algorithmically, that would be awesome. That would be, I think, that would be, that would have actual practical value in some sense, for sure. Yeah.
Thanks.
So Jeff, that you know, I think Carla mentioned all of the questions in some sense. So we've, so that essentially, you know, that we've not. This is pretty much at this point in time we have, you know, if we could answer some of the questions that Carla is saying, that would be nice, but we don't know how to answer them in some sense. And I think going back to the computations, I think. Maybe if there's a way to do things sparsely, as you said, with only the terms needed, that would be really nice. I don't know right now if I have an answer to that, but so I have to think about it. I don't know. I don't have an answer. That would be a really nice direction. I agree with you. That would be nice.
I mean, this is like when I looked at this, like I only added the cuts I did like explicit enumeration if there was a dense submatrix in the queue, like say on the 3 variables,
right?
Then I would just check that 3x3 matrix like explicitly,
right?
And then add the inequalities, and I did that up to like 3x3, 4x4,
right?
5x5, and then at a certain point, then like it gets less and less likely that you'll get all 6 of the or 5 of the.
Right, but I feel like the sort of the stuff that Ruth did, Ruth and Radu and these guys, where I mean, I feel like maybe that is because they use machine learning, it gets hidden. But I feel like that's probably something that's happening. We don't understand enough the features there, obviously. You know, but I agree with that. There's something like that is happening, and again, their results are in fact even more. Like to me, that was really very inspiring because. You know, we are doing 25% sparsity, right, for these instances. They were doing 3x3, and they essentially closed a lot of the gap, like on 100 by 100 matrix. I mean, that is incredible. And you know, someplace the constraint matters. So, like for example, in the OPF case, right, where you can replace the SDP by SOC, and you get basically sort of very tight bounds. There are some good theoretical reasons to explain that because, that's more to do with these methods of decomposing SDPs, right? So, if you only have this term and this term and so forth, and like this sort of, but I think that's why that seems to be working there. but like, 25% sparsity randomly done for this Q matrix, and then 100 by 100, and then you just do the 3 by 3s like these guys did, and they close most of the gap. That is just like, yeah, it's just, I don't think the theory can explain that. It's just, yeah, I wish we could. And I think, again, maybe this is related to what Carla said, that these are just really worst case results. So really, it just turns out that, these cones are actually not so bad in most directions. So maybe maybe that's actually a very nice question. Maybe doing a uniform or something like that would be nicer. Uniform, like average distance in all directions. Yeah.
Are there any other questions? Okay, so thank you, Professor Day, for the wonderful talk.
Thank you very much.
Uh,
Thanks, Jeff. Appreciate all the questions.
So